Scott is the James Clark Professor of Bioengineering, Mechanical Engineering, and Orthopaedic Surgery at Stanford University, where he also received his master's and Ph.D. degrees. His research is driven by the desire to improve the treatments of individuals with physical disabilities. And to the dynamic walking community, he's probably best known for his instrumental contributions to developing simulation tools for the modeling and analysis of animal and human gait and disorder. But, as I learned, he has also made inventions in the areas of microscopic endomicroscopy, correct? Yeah. Sorry. Surgical navigation and optogenetics. So with this breadth of research capacity and knowledge, it's no surprise that he has been the founding chair of the bioengineering department at Stanford and received numerous awards for his research, including an award for which he was honored by President Clinton. And tonight, he will focus on insights from simulation of human movement dynamics to gait and disorder, I believe. So please help me welcome Scott Delp.
Thanks, Hartman. Pretty fancy place we got here. It's just such a pleasure to be here. Good evening, everyone. I really wanted to thank Steve and Hartman and Chris and Art and all the organizers for putting on a great meeting. I'm really excited to be to the conference and learn from all of you. And it's special to be here with my son Quincy, who's an amazing young musician and kinematician, to have him experience the creativity of this group. So we're in Carnegie Music Hall, so we should start with some music. This is the Chopin Scherzo No. 1, performed by Quincy Delp. So I work at home a lot, so I've heard that piece before. It gets played many times a day. Never that fast. I think there was some adrenaline happening. You think? So I'm grateful for the opportunity to share some insights into human movement dynamics that we've gained through simulation. Moving is essential for health and well-being, and when mobility is lost from injury or disease, it's a devastating blow. And my goal has been to gain fundamental insights into the dynamics of locomotion and to design devices and treatments that prevent injuries, improve mobility, and optimize human performance. And computer simulations play a key role in achieving this goal. Walking in a crouch is challenging. The energetic cost is roughly equal to climbing stairs, and the high forces in joints can lead to joint disease and pain. A crouch gait like this is the most common walking abnormality among individuals with cerebral palsy. Now, this boy was fortunate to be treated at the Gillette Children's Hospital in Minnesota, where he received a set of surgeries, including a distal femoral extension osteotomy and a patellofemoral advancement that dramatically improved his walking ability. His gait's not normal, but it is much better than before surgery. This is a fantastic outcome made possible by a very creative and dedicated team of surgeons who invented this procedure, engineers, physical therapists working together to gain insights and develop new treatments. Unfortunately, crouch gait does not always improve after surgery. We've analyzed hundreds of patients with crouch gait before and after treatment at several major and excellent clinical centers, and roughly half of them get better. Many don't, and some get worse. This is because the causes of crouch gait are unclear, and as a result, it's difficult to design treatments that will consistently improve walking ability. Okay. I'm going to try again. So can simulation help improve our understanding of crouch gait? And if we have improved understanding, does this improve treatments? Well, the answer is yes, and I'll show this to you. The other question is, can simulation enable studies that are not possible with experiments alone? I'll make the case that simulation is essential for understanding muscle actions in normal and pathologic gait and can provide insights that are not possible to achieve with experiments alone. Almost every complex product is designed using simulations. Airplanes, for example, are simulated and analyzed before they're built. This bit of history, a modern stealth aircraft, first became possible when an applied mathematician working for Lockheed in the late 70s developed a computer program called Echo 1, which made it possible to predict the radar signature of an aircraft made from flat panels. So simulations like that are used broadly in engineering design because they work better than trial and error. Imagine the cost of building a set of airplanes and crashing them until you found one that worked. But this is essentially what we do in medicine. Very little in the biomedical industry and in medicine is designed using simulation. Drugs, not many examples designed with simulation. Devices, rarely. A little bit of testing, but very few are designed with simulation. Surgeries, there are just a few examples. This is true because it is more difficult to simulate the motion and biology in a biomechanical system than it is to simulate the physics of engineered systems. Our goal is to change that by providing simulation tools that provide accurate simulation results of human and animal biomechanics. And we're motivated to do that because simulations complement experimental analyses of human movement. You can, of course, use simulations to visualize complex movement patterns. You can see the joint angles, ground reaction forces, EMG together. And of course you can do that, but I don't want to pass by it too quickly. If you aren't visualizing your data, you're probably making mistakes. I've visualized data from lots of excellent papers and even our own simulation results, and you can find obvious errors, feet going through the floor, muscles going through bones, and so visualization is quite helpful. you can estimate parameters that are difficult to measure, muscle forces, joint forces. So if you want to design a gait, for example, that reduces joint loads, it's very difficult to make those measurements, but you can estimate them in a simulation quite easily. It allows you to do design studies, for example, simulation-based design of protective technology or technology that can enhance your performance. And you can establish cause-effect relationships. If I want to know which muscle is causing what motion, and you have a description of the physics and biology, you can establish those cause-effect relationships. So I'll organize the presentation around a set of examples. The first one is a design study in which it's not designing a device, it's actually designing a gait that reduces knee loads for individuals with early-stage osteoarthritis. So that's the first example. The second one is using a simple musculoskeletal model to estimate parameters, just like a musculotendon length, that's difficult to measure. And I'll show you how that can be valuable in clinical decision making. And the third example is really a set of examples where we analyze the actions of muscles in walking, running, and crouch gait and establish cause-effect relationships of which muscles are actuating the motion. So I'll go through those three examples, and then what I'll do is close the presentation with a set of challenges. And I think that'll lead in, hopefully, to a lively discussion at the end about what are the challenges for our field, what are the opportunities, what should we be doing with our lives, and how can we spend our resources that we can really enhance mobility. So I hope keep those ideas in mind as we're going through other challenges that we might face as the field and also what the opportunities are. So let me begin with the first example that was launched initially by B.J. Fregley. His goal was to design a new gait pattern using simulation to reduce the load on the knee for patients who experienced pain. And BJ was motivated to do this about 5 years ago. He and Jeff Reinbold published a paper in which they used simulation to optimize gait to minimize the load on the medial compartment of the knee. So about 85% of osteoarthritis happens in the medial compartment. So the inside of the knee is much more commonly subjected to osteoarthritis. And he developed a set of different gait patterns where he was trying to manipulate this ground reaction load and its relationship to the knee joint to see if he could reduce the load on the medial side of the joint. Now, I'm showing here a frontal plane view of 5 different gaits. It's a little tricky to see the differences, but I'll show you them in detail. But what I wanted to do was give you the bottom line. They discovered in their simulations that it was possible to reduce the knee loads, the knee adduction moment in particular, which is related to the medial compartment load, by about 40%. So that's a huge reduction. That's about the level of reduction you get from a big surgery. So taking a little bit closer look, so here is the nominal gait, and you see the ground reaction force headed a certain distance medial to the knee. And here's a slightly modified gait. You can change the medial compartment load by changing the ground reaction force or its relationship relative to the knee. And this gait didn't change the magnitude of the load, but it changed its position relative to the knee. And BJ published this about 5 years ago and developed this medial thrust gait, he called it. So it was pretty cool. He used simulations to design a new gait, and he was motivated because he had knee pain, and he wanted to figure out a way to walk that would reduce his knee pain. So we had a simulated gait that I'm showing here that could reduce your knee load, and then BJ learned how to do the gait. So he could walk this way. So here's his walking ability, and this is the simulation that predicted the knee load. And indeed, even in the measured gait, he could reduce the knee adduction moment by about 40%. Okay, so if you look at this gait, what you notice is there's a lot of pelvic movement. I can't do this gait. I've tried. BJ's tried to teach me. He's really good at his pelvis motion. He can move his pelvis and torso, and he crouches down a little bit, moves his knee medially. And he can walk around Disneyland with his kids, and he doesn't get any knee pain. And that's awesome for BJ. It turned out it's hard to teach this gait to other people, but it inspired us to try to come up with a simpler gait adaptation that might achieve the same goal but be more learnable. And so Pete Shull was a graduate student at Stanford, and he went about designing a gait retraining program for 12 subjects who had early stage osteoarthritis. So here's an x-ray of one of the subjects of their knee joint. You see over here on the lateral side where the fibula is here, there's a nice space in the joint, and that's because you have a nice thick layer of cartilage. On the medial side, it's beginning to wear out, and these almost have bone-on-bone contact. So the idea is to reduce the load that's compressing this by applying an adduction moment that is going in the other direction. So that was Pete's goal, and what he did was he was into haptics, so he put a little haptic vibrator on the tibia. This is after about 3 years of figuring out other ways to do this, so I'll give you the short story. And he gave some people suggestions on how to modify their gait. And they did it quite easily by changing their angle of their tibia. We instructed them just to toe in, and this toe-in angle decreased this knee adduction moment. So here's their baseline walking. Here's their toe-in angle. So here's his toe out a little bit, toe in a little bit, and it changes his tibia angle a little bit. It's very easy for them to do. And they were very motivated to do it because when they did this gait over a period of time, their knee pain got better and their function got greater. So if I'm showing you a plot here of the knee adduction moment, so here it is versus percent of stance, here's their baseline. And here is a subject with just a toe-in gait. And in this case, there's about a 15% reduction. On average, we had about a 20% reduction. So it's not the 40% that BJ got, but it's still a good reduction in this knee adduction moment. So that's great. You reduce the knee adduction moment. So what? The good news was that we assessed their pain on a visual analog score. So here's their visual analog knee score. Here's their baseline score, a little above 3 on average, pretty variable. Some subjects hurt more than others. We had them come back for 6 training sessions. It turns out they could learn this gait in about 4 training sessions. We had them come back 6 training sessions, and then a month after the 6th training session. So here it is post-training, 6 weeks later, and here's a month follow-up after the last training session. They were able to retain the gait, and their pain was reduced relative to their pre-training score. Now, there's a strong placebo effect in these kinds of studies, and we estimated how big the placebo effect was. This is not quite double what you'd expect from a placebo effect, but it's about 75% more than placebo effect. So I like this. It was a nifty study because BJ did this simulation-based design of a gait that turned out to inspire a whole set of studies, not just in our lab, but in other labs to do these gait adaptation studies. And it resulted in a relatively simple wearable haptic device that could teach people how to develop a stable gait that would reduce their pain in early stage osteoarthritis. Okay, so that's the first example. The second example is related to hamstring lengths and crouch gait. And this was done with a set of collaborators led by Allison Arnold, and Mike Swartz was key, as well as clinical collaborators at various hospitals. And we were interested in the treatment of crouch gait because it is so challenging. I said at the outset, this is a gait abnormality that's very common among kids with cerebral palsy. About half the kids get better after treatment and half don't. The reputed cause in many cases is contracture of the hamstrings, that is shortened muscle fibers, that when they're stretched, they develop passive force and limit knee extension. Another possible cause is hamstring spasticity, so exaggerated stretch reflexes. If the muscle is stretching and the threshold for the reflex is lower, you could get excessive force, and that might limit knee motion. So those are the reputed causes, and many of these subjects have hamstring lengthening surgeries, and some of them get better, some of them don't. So we asked whether, using a simple musculoskeletal model, if analyses of muscle tendon lengths and muscle tendon stretch velocities could help in understanding the cause of crouch gait and planning surgical interventions. So we measured 3D gait kinematics in about 150 kids with crouch gait and a whole set of unimpaired children. We used the musculoskeletal model to calculate the musculotendon length of hamstrings and other muscles. And what I'm plotting here is the normalized length, so it's the length normalized to the upright standing position. We do that so we can compare subjects of different size. And this is the length versus percent gait cycle. And this is the velocity versus percent gait cycle. So then the question is, if somebody has a crouch gait, is the length shorter, is the velocity slower? If the length is shorter, perhaps then it's hamstring contracture causing the crouch gait. If the velocity is slower than normal, then perhaps it's spasticity. So we see some cases where instead of reaching this peak velocity in early swing, the hamstrings start to stretch and then are cut off. They don't stretch any faster than that. And in that case, you might suspect hamstring spasticity. Okay, so the other question was, if they were short and they had a hamstring lengthening surgery, did they get longer? And if they were slow and they had a hamstring lengthening surgery, did they get faster? So all of these kids are candidates for hamstring lengthenings. At some hospitals, about 95% of people who walk in with crouch gait get a hamstring surgery. At other hospitals, about 15 or 20% get a hamstring lengthening surgery. So there's huge variability. So it wasn't known whether those surgeries actually made the muscles longer or faster. So we wanted to answer that question. And then if they did they get better? So did their knee extension improve? Because that's the basic goal of treating crouch gait. Okay, so we estimated musculoskeletal lengths and velocities by measuring 3D gait kinematics, having a musculoskeletal model, and then plotting this for the 150 kids. So how many subjects walked with short or slow hamstrings? There were about a third, 30%, that had hamstrings that were slow. They reached normal length, but they didn't reach the normal lengthening velocity. There were about a third, if you take these two pie pieces, that were short. Most of them that were short were also slow. If they had short hamstrings, the hamstrings lengthened more slowly than normal. And there were a few that were just short but lengthened fast enough. And then there were about a third, 34%, that had hamstrings. They were crouch gait subjects. They walked with excessive knee flexion of at least 20 degrees, but their hamstrings were neither short nor slow. Many of the ones that were not short or slow had surgery, and some didn't that were. So the question is, did they get longer and faster after surgery? So if they were short, they tended to get longer. If they were slow, they tended to get faster. But if they were not short and not slow, and even if they had a surgery, they didn't get longer or faster. So that was good to know. Then did they get better? Were postoperative knee extension related to these hamstring lengths and velocities? I'll show you some statistically significant findings with these case examples. So here's a subject I just showed you. Her hamstrings were short and slow. She had hamstring lengthening surgery. Her hamstrings then lengthened to a greater length and faster, and you can see she had improved knee extension. So in general, that was the case, that if they were short and slow and they had a hamstring lengthening surgery, they got longer and faster, and they had improved knee extension. That's good. The opposite was also true. Here's somebody who had short hamstrings. He also had other balance problems. He did not have a hamstring lengthening surgery. He had some other surgery. Here he is after surgery. His hamstrings are not longer. They're not faster. They probably need to be to walk normally, and he has unimproved knee extension. So that was the case. There were a whole set of patients that had short and slow hamstrings. They weren't treated. They didn't get longer or faster, and they had unimproved knee extension. There were also subjects that their hamstrings weren't short and slow. They had hamstring lengthening surgeries, and they were at risk for developing increased hip flexion and anterior pelvic tilt, a side effect of the surgery. But that was only a risk if their hamstrings were not short and slow and they still had the hamstring surgery. So that's a simple analysis. It was quite useful. You can make these computations in real time. Actually, if somebody's walking through the lab, you can calculate their hamstrings lengths and velocities. And as we've made the software available, and it's now used in dozens of clinical centers as part of the treatment planning paradigm. So it's not the whole answer. It's certainly not the whole picture. You can't predict who's going to get better from surgery from a simple measure of musculoskeletal length and velocity, but it's an important thing that you can get out of the model that you can't get from experiments alone. And certainly it's valuable to know whether a particular muscle that's a candidate for surgery, a muscle lengthening surgery, is short or slow. So I wanted to tell you that story because it's a relatively simple model, and it's a long story. It started a long time ago when I met George Rabb, an orthopedic surgeon, who also knew how to program a computer, and he was making these calculations for his own benefit. And then we started making it on more patients, and that was like 20 years ago. So the story to translating into hospital where it's in routine clinical use has taken a long time. So some of you may have heard parts of this before, but the story is still alive, and people are now doing this in clinics. Okay, so the third example is analyzing the muscle actions in walking, running, and in crouch gait. So to do this analysis, where we're trying to establish cause-effect relationships, we need a more sophisticated musculoskeletal dynamic model. So what are the elements of the model? You need some way to control the many degrees of freedom of walking and running and crouch gait. You need a model of muscle tendon dynamics. Matt Millard just published a paper this year that was inspired by the 1989 Zajac paper and those models, where we tested whether or not you could estimate forces reasonably well with a Hill-type muscle model. There are certainly limitations to Hill models, but what we did in this paper was take experimental data that's available in the literature from Northwestern University, and in those papers, they have a pattern of excitation, they have a set of muscle lengths and velocities, and they calculate and measure the muscle force. We input the same pattern of excitation, muscle lengths, muscular tendon lengths and velocities, and you get pretty good agreement, errors between 10, 15, in worst case 20%, with Hill-type models for pretty complex force length velocity relationships. So that's the model that we typically use that gives reasonable estimates of muscle force, but has many limitations that I'm sure you're aware of. We also need representations of musculoskeletal geometry, and we use a SimBody dynamics engine to generate the equations of motion so we can calculate the accelerations given forces in muscles, gravity, centripetal Coriolis, and external forces. And if you have a reasonable controller, you can generate highly realistic muscle-actuated simulations of walking. So this one was developed by Chand John. It's a simulation of 10 gait cycles that track experimental data. So the input to this is experimental kinematics and ground reaction forces. Computed muscle control algorithms finds the pattern of excitations that drives the dynamic model to match the experimentally derived kinematics. And it matches very well. So you can generate highly realistic simulations of individuals walking and also, because it's stereotypic, average walking. The patterns of excitation generated by the controller match EMG data very well, and then you can use these models to query muscle function. So this allowed us to ask a fundamental question, which is, how do muscles contribute to support and progression over a range of walking speeds? So what do we mean by support? I mean body weight support. So if you're walking normally, you need to support your body weight. If you're walking in a crouch, you also have to support your body weight. So we're interested in which muscles are going to provide body weight support. And because crouch may be a result of insufficient body weight support or muscles that are actually pulling you down to the ground being overactive. So we characterize support as the vertical acceleration of the mass center in the upward direction, and progression as the fore-aft accelerations of the mass center. And we wanted to do it over a range of walking speeds, and Mei Lu, working with Clay Anderson and Mike Swartz and I, developed this very small army of simulations, 8 subjects walking at 4 speeds. We've tried to make all these simulations available so that others can reproduce these results. So if you go to simtk.org, you can download any one of these simulations and you can analyze it for yourself. You can reproduce our results, you can estimate muscle forces, you can do whatever you want with this simulation. What we wanted to do was understand how it provided body weight support and progression and how that varied with speed. And we did that by analyzing how muscles contributed to the ground reaction force. So here's a plot of the ground reaction force. So the vertical force is here, horizontal force, so this is back-facing, forward-facing. And so this is the force on the ground, and that determines how the mass center accelerates. We can estimate the contribution of a muscle to ground reaction force by making a very small change in muscle force determining the change in the ground reaction force resulting from that, and computing the net change in the mass center acceleration. If we then multiply that dF by the estimated muscle force, you get the change in the ground reaction force resulting from a particular muscle. You can do this with springy interactions between the foot and the floor, or rigid interactions, which is what we've been doing more recently with a constraint that was developed by A.J. Seth and Sam Hamner. Okay, so we can develop a simulation, and we can analyze a simulation to see what a muscle's doing, and then you can get some obvious conclusions. For example, like the quadricep, vasti, support the body weight. So if you, not a big surprise, if you turn on the quadriceps, it extends the knee, it generates a ground reaction force, and that pushes your mass center upward. So that's good, it reproduces things that we think are true. Interestingly, not only does it extend the knee and push your mass center up, it also changes the values for all the other joint angles because of the intersegmental resultant forces. So let's look at the quadriceps in a little bit more detail. So the vasti I'm showing here in the quadriceps, and this is the plot I just showed you for free speed. I'm going to show you for fast, slow, and very slow walking. And what's plotted is the acceleration of the mass center in meters per second squared versus percentage of gait cycle. So here's the ground reaction force here. The quadriceps are on early in stance. They generate a large vertical force, and they slow you down. So when you walk faster, they do a little bit more of the same thing. When you walk slow or very slow, they do almost nothing. The EMG activity of the muscle gets greatly diminished, and they produce smaller forces, and they produce a very small acceleration. Well, if the vasti aren't doing it, something has to do it at those low speeds. And what is it? Well, when you walk at low speeds, you look a lot like a passive dynamic walker. You walk with extended knees. So here's the knee flexion angle versus gait cycle for fast walking. So the knee flexes fast, extends, and then flexes a lot during swing. In slow walking, you essentially walk with an extended knee. So the skeleton can provide body weight support. When your knee is fully extended, the skeleton, the passive skeleton, can provide a fraction of body weight support that is not provided by the vasti. Gluteus maximus, it operates at relatively the same time as the vasti, and it does about the same thing. So it generates a vertical ground reaction force at free speed. So you can see that here. Of course, we go to mid-stance. We excite the gluteus maximus. We see that it, of course, extends the hip, it extends the knee, and it generates a vertical ground reaction force that's not shown here. But that's the ground reaction force shown here. At fast walking speeds, it does more of the same thing. At slow walking speeds, it's diminished. Again, because we get passive support from the skeleton. Okay, what about soleus? Soleus is one of the big plantar flexors. It is on in late stance, so it's on just a little bit in early stance. There's a burst of activity in late stance, and it is one of the prime movers that generates a ground reaction force in late stance. If the soleus is paralyzed, so here's a simulation in which we just turn soleus off, you see that the knee is flexed. So the soleus, even though it crosses just the ankle, is important for generating a vertical ground reaction force. If you turn it off, the limb collapses in late stance if there are no compensatory activities of muscles. One of the biggest causes of crouch gait is weak plantar flexors. It's highly correlated with crouch gait. And when people have strong plantar flexors, they tend to get better after treatment, and it's because the soleus and the gastrocnemius provide body weight support in late stance. It's important for extending the knee as well as plantar flexing the ankle. A little bit less at very slow walking, a little bit more at fast, but it's not like the vasti that shut down. Right? The vasti essentially shut down when you walk slowly. The plantar flexors retain significant EMG activity and have an important function. So soleus supports your body weight and propels you in late stance. So this computational model enables you to access, I showed you 3 or 4 muscles, There are 92 muscles in this simulation if you count both legs. And you can query the actions of those muscles. This simulation is also downloadable at simtk.org. And any of you are welcome to do any set of studies with this model. You can test it, reproduce the results, try to disprove it, anything you'd like. Okay, so that's walking. What about running? AJ Seth and Sam Hamner developed this very nice model simulation of running and analyzed muscle function in running. One thing to note is that muscles support your body weight and propel you forward. So here's the ground reaction force in running. Again, acceleration in meters per second squared. If you count gravity as about 10, this is about 2 body weights. So this is running at 4 meters per second. So relatively slow mile pace versus percentage of stance phase. Here's the ground reaction force in gray. Here's the sum of the ground reaction forces generated by all the muscles. And you see muscles are essentially providing everything. There's a difference here in early stance, and that's basically an artifact of the contact model that we use is insufficient to capture the first reaction forces in stance. So the soleus is on, generates high force. It supports your body weight, propels you forward, just like it does in walking. Vasti are on, simultaneous with soleus in running. Remember in walking, the G-max and the quadriceps came on early, soleus was off, and then later in stance, soleus comes on to propel you forward. In running, you don't have enough time where your foot's in contact with the ground for that to take place. So the muscles come on at the same time. They both produce vertical support that help you bounce off the ground, but they have antagonistic activity in fore aft. Soleus propels you forward, vasti slows you down. What about crouch gait? Cat Steele developed a set of simulations of crouch gait. And interestingly, the actions of muscles in crouch gait are very similar to what they are in running, in that even though you're walking in crouch gait, your foot's on the ground for a long time, so there's plenty of time for the quads to come on and then shut off, and then the plantar flexors to push you forward. But that's not what happens. The limb is bent. There's no support from the skeleton. All of those extensors come on as soon as your foot contacts the ground, and there's antagonistic activity of the vasti and the plantar flexors that produce a very inefficient gait and much higher muscle forces and much higher joint forces. In severe crouch gait, it can be 2 or 3 times normal, and that high force leads to thinning of cartilage and knee pain that's typical in older kids with crouch gait. Okay, so that's the set of examples. What I want to close with is a set of challenges for the field. I've listed 5, I think. There are about 93. So I'll seed the conversation with the 5 challenges. And I welcome anyone and everyone in the open session to bring up other challenges and comments and opportunities. So one challenge is modeling muscle tendon dynamics. I said that we have reasonable models of normal muscle. They can be better, but we have lousy models and very little understanding of pathologic muscle. We're trying to gain insight into that with advanced MRI techniques. Mike Llewellyn, who was a student in my lab a few years ago, developed this microendoscopy technology. Shown here, this is a 0.3 millimeter microendoscope. And with that, if you insert it into muscle, you get these nice pictures of sarcomeres. You can equip the end of this microendoscopic probe with a microstimulator, and you can stimulate and record at 500 hertz, and you can see the sarcomeres contracting in humans. So our goal is to try to figure out what's happening to sarcomeres in cases of cerebral palsy and stroke and aging and training. So this early study was done a few years ago. It used a big 2-photon system that was very expensive. Gabriel Sanchez is a graduate student who just finished his Ph.D. who's turned this into a much smaller handheld wearable microscope that we're now using for clinical studies. So this is one big challenge for the whole field, is to have better models of muscle tendon dynamics. And I would argue that what we need is not just fancier models. There's lots of fancy models. We need models that really work, that you can compute with and that compute forces and other parameters that are compared to benchmark experimental data that have sufficient accuracy to answer the scientific questions that we care about. Okay, challenge 1. Challenge 2 is reproducing simulation results. There are hundreds of published papers in the literature that use simulation, mine included, many of yours included, where it is impossible to reproduce the results. No one can do it. The code's not available, the models aren't available, so all we can do is read your paper and believe you because you are a good writer and a reliable person. So I would say that it is better if you could make your model and simulations available so that others could reproduce and build on your work, because reproducing scientific results is the basis of science, right? We need to build on things. So we've been trying to take a stab at enabling people to reproduce simulation results at this website, simtk.org, where the OpenSim project's hosted. There's lots of projects hosted. If you have a model or just some results that you want to host there, it takes about 5 minutes to set up a project, and you can host your data here. So in addition to software, there's a repository of models. So Edith Arnold developed this nice low extremity model. Sam Hamner has this whole body model and simulation results. There was a model of the lumbar spine developed at UCSF in Berkeley. There's a model of the shoulder that's under development that's posted there that people can download. So that's nice because it takes years to develop these models, and you'd like to focus on doing some scientific studies, not just on model building. So if you're building a model of a finger, of a shoulder, of anything, and you want to post it, you're welcome to post it here, and you can track who's downloading, who's using your model. It's quite a nice way to get your results out there. So when you do have a model or data or some tool you want to make available, there's this repository. So OpenSim is one of the 70 projects on simtk.org with downloads. There are about 17,000 users just of the neuromuscular biomechanics projects. So that means 17,000 different people have gone and downloaded something. So if you have something you want to make available to people, there's lots of people that would want to use it. So here's the lower limb model, the spine model. There's the MATLAB interface that Jeff Reinbold developed. And there's lots of people using this. We're trying to develop a community of people who actually contribute things and test the software and models so that we could advance the field more quickly. I should say, given the OpenSim workshop yesterday, it's not easy. It is much easier to do your stuff at home and not let anyone else see what you do. Making it available is hard, especially when you get all excited about things and you want to show what you just did last week to the whole crowd, and all that stuff works. You just got to get your MATLAB going. So hopefully people will crank through that and have a good time using the MATLAB interface to OpenSim. You too can be part of the worldwide community. Okay, a third challenge is modeling neuromuscular control. So Marcus Pandy and Clay Anderson developed this really nice paper about 13 years ago where they did a dynamic optimal control problem for walking that took roughly 4 months of computer time. That's not practical for most graduate students. Clay was incredibly dedicated and did complete that. But Daryl Thalen, and working with Clay and me, developed a computer muscle control algorithm that now you can compute controls in roughly 10 minutes, sometimes 5 minutes, sometimes 20 minutes. But it enables you to generate small armies of simulations so that you can do statistics on simulations. So that's a tracking controller that lets you develop a simulation of an individual subject and then probe the model to try to learn something. More powerful is predictive control. And Jack Wong developed a predictive controller for walking and running in which we developed biologically based control laws based on the reflex models of the Geyer and Herr paper that inspired us, where we didn't have to use any motion capture or animation data to generate these simulations. And the key was biologically plausible actuation. So the state of the art in computer graphics in the SIGGRAPH 2010 paper was shown here. Pretty good, but it doesn't look very natural. Our hypothesis was that using biological actuation, we would get more realistic walking. So the optimization, I'll show you at various phases. So here's early in the optimization. At 50 iterations, you're getting walking, so it doesn't fall, but it's kind of a clunky behavior. If you compared these to experimental data, that wouldn't look very good. The torques would be wrong, the excitations would be wrong. But after 3,000 iterations at a self-selected speed of about 1.25 meters per second, you get a good simulation. So here's a 3 meter per second running, drunk running here, 500 iterations. And then again, at about 3,000 iterations, it converges on a reasonable running pattern. The arm swing just comes out. We don't prescribe any of this. It's just to balance the angular momentum of the legs. So here's a comparison to the this was slow walking before, and here's a slow walk here. Much more realistic walking. Here's the happy walk. If you're ever feeling down, just walk like this. Here's very fast walk if you're really feeling down. But here's the result that gives very good reproduction of experimental data. You can try different objective functions. So here's the sum of square joint torques. You get a little bit of a crouch gait. The best we had was minimizing metabolic energy expenditure. So there's some aberrant activation of tibialis anterior and some other problems when we use the minimizing torques. So here's sum of squared activations, and you get definitely a crouch when you use this criteria where the metabolic cost is better. So the gait was typically more crouched and less metabolically efficient despite low activations. So once you have a predictive controller, you can change muscle properties. So we can weaken the plantar flexors, and what happens is you get a crouch gait. And like I said before, weak plantar flexors is a likely cause of crouch gait in many subjects. And if somebody has weak plantar flexors and you lengthen their hamstrings, they're not going to get better. If you weaken their hamstrings, they walk with this knee hyperextension, which you frequently see after hamstring lengthening if not done appropriately. Here's normal gait, and here's the hyperextension of the knee. So here's weak quadriceps, weak vasti, and you get a kind of a quads avoidance gait. You can walk with essentially no vasti if you just keep your knee extended and use your skeleton to support your body weight. Those nominal simulations are not very robust. You have to train the controller by applying external forces. So there's a 100 Newton force there. But if you train the controller with external forces applied over a relatively short duration, 0.4 seconds, it adapts a gait with a lower center of gravity that is more stable. It's less like normal walking, but it's more robust. The running simulation was even more robust to these same perturbations. Jack did a beautiful set of work where he trained it to walk on ice, and it adopted different gaits for that. This same controller can generate both walking and running, and at different speeds. So this is just cranking up the walking speed. We had a hard time at the walk-run transition, so you won't see a speed of 2 meters per second. It's going to go right from a fast walking of 1.75 meters per second to running at 3 meters per second. 3.5. So we just command the forward speed, and it generates the excitations that produce the running at that speed. When we compare the excitations, the joint moments, the ground reaction forces to experimental data that weren't used to generate the simulation but are just independent, you get quite realistic simulations of running. So that is not yet implemented in OpenSim, but Tim Dorn and Jack Wong are working on implementing that predictive control in OpenSim. And we'd love to have other predictive control models that are available to others. Okay, challenge 4, testing simulation accuracy. Before you can gain insights, you want to know what the limits are of your simulation. And we test things by comparing the simulation result to joint angles, to joint moments. We can get joint moments from inverse dynamics, and we can also calculate joint moments by summing up the muscle forces in their moment arms and calculating them that way. We can generate ground reaction force and compare those to experimental data, compare experimental EMG to our muscle activations. And in some cases, we have measured subjects with instrumented implants, so we can calculate their joint forces and compare those to the calculated joint forces to the experimentally measured joint forces. And it's really essential to do a robust set of comparisons so that you can understand the strengths and the limitations of your simulation and whether it's appropriate to use for a certain set of questions. The final challenge I'll pose is predicting clinical outcomes. I said at the outset we're interested in improving clinical outcomes, and I just wanted to highlight one study from Jen Hicks, published just 2 years ago, where she showed that insights gained from simulation, in fact, when surgeries are made consistent with those insights, in that you could predict the outcome of the surgeries done to treat crouch gait with roughly 75% accuracy. So given a relatively small number of parameters identified in biomechanical studies, some experimental, some simulation, you could predict the outcome of crouch gait with 75% accuracy. There were still some false positives, still some false negatives, but the 75% is much better than the 48% of kids who actually got better from the surgery. So we could identify a class of subjects who were likely not to get better and those that were very likely to get better from surgery with the biomechanical principles developed with simulations. So I challenge all of you, there's an incredible amount of technical talent at this conference, incredible level of creativity, and to channel that to try to improve mobility for people who have physical disabilities is something this community could really have a huge impact in the coming years. So with that challenge, I'll just close by thanking funding sources, the NIH, that makes the world go round, and DARPA, we get funding from them, as well as the Physiome Project, as well as my excellent colleagues back at Stanford who do all the great work. Thank you very much. Good, lights coming up. I would say just go for questions from the audience. The acoustics are pretty good, so comments, questions? Yes, please. Yeah, so the question was, do we have rear foot strike and forefoot strike with changes in speed? So the maximum speed of JAX simulations with the predictive control was 5 meters per second, and those simulations didn't have forefoot contact. SAM's simulations were based on 12 subjects, 3 of whom were forefoot contactors, and those simulations, they didn't make a transition unless the subject made a transition, and in those 3 cases there was simulated forefoot striking. We don't yet have a predictive controller that will do that as you increase speed, make a transition, but that would be cool. Thanks. Yes, please. Yeah, I didn't get into that because it's a long story, and there's an excellent paper that got published last summer that describes that. But yeah, okay, sorry about that. The question was, what are the details of the predictive controller, or at least some of the additional information? We were inspired by the Geyer and Her paper that had simple reflex rules, and that was the basic structure, along with a dynamic optimization that had the criteria of the commanded speed not falling down and and minimizing metabolic cost to distribute the actions of muscles. And so it was a big computational problem. They certainly don't run in real time. It takes weeks to compute the answers on these, and so we're using clusters because it's a dynamic optimization problem. That's the basics. To go to another level of detail, I just have to refer you to the paper because it's all written down, which algorithms and all that kind of stuff. Happy to send it to you. Yes, please.
Your first example of the gait adaptation, what do you use to drive the haptic feedback?
Yeah, good question. So the question was, what do we use to drive the haptic feedback for the example of the gait adaptation? So we had subjects walking on an instrumented treadmill, and we have the ground reaction force, and we have the positions of their knee markers, so we know what the knee adduction moment is. And when the knee adduction moment got big, we'd give them a little buzz to move their knee medially, basically. We gave them some tips. So early in the study, we said, you can do your trunk, you can move your knee medially, or you can rotate your foot. And people all adopted the foot rotation thing because they didn't like doing the trunk lean. And then that was a stable gait pattern. So we actually had real-time measurements of force and knee position, and we could calculate the variable that they were manipulating. And we just gave them feedback of the variable, and they changed it on their own. Does that make sense? They came back, so they came in for the training session. We had no feedback, and then they came in for 6 training sessions. And we measured essentially the learning curve, and after 4, they didn't change. And then for a month, they had no feedback, no training, and then they came back in and walked on the treadmill with no feedback, and they had retained it. So that was good. Yes, please. Yeah, so the question is, crouch gait could come from a short hamstring, weak plantar flexors, tight hip flexors, poor balance, bone deformities. That's an extension of the question. What about the model let you differentiate short hamstrings from weak plantar flexors? Yeah, so the data we got from the patients were kinematics, and that's essentially all we needed to calculate the hamstring's musculotendon length. So from the joint angles in a musculoskeletal model, we can calculate the musculotendon lengths and velocities. The plantar flexion weakness comes from 2 things. One is we calculate the plantar flexion moment, and we can compare that to normal. And also there are manual strength tests, 5, 4, 3, 2, 1, where 5 is full strength, 1 is incredibly weak. And so we have those data too. So it's not a perfect measure, but those 2 things, the ankle moment and the 1, 2, 3, 4, 5 manual muscle test, let us determine who was weak and not. Yes, please. Yeah, so the question is, was there a 1-to-1 correspondence between the hamstring getting longer and faster and the gait getting better? And the answer is no, because there were some instances where the hamstrings were normal length and normal velocity, but the gait was still bad. And the hamstrings didn't need to get longer and faster. It was plantar flexor weakness or a bone deformity. And if those things were corrected, the gait tended to get better, but the hamstrings didn't get longer or faster. Yeah, so that's a good question, is how did we know what got better? And I glossed over that. And we've done a bunch of different ways. One way to do it is there's a normalcy index that is a statistical model that gives you one number of how normal is, how normal your gait is based on, and you can tune that to be related to the knee, and we tried this normalcy index. We've done that in a study or 2. This one was just how much knee angle changed. And if the knee angle got within the normal range or got improved by 10 degrees, we call that an improvement. So we just did improved or not improved. And in fact, the conclusions were not sensitive to the specific outcome measure that we used. So we just had this change in knee flexion angle because that was the goal of the surgery. Yes, please. Yeah, so the question is, what are the clinical applications of predictive control? Well, I can think of a few. The gait design scenario was kind of it was an inverse model, but it's kind of predictive, right? He predicted a gait that would, B.J. Fregley predicted a gait that would reduce knee load, and that was an important clinical question, and so that's one application. The other is, if you're developing, for example, a wearable robot, let's say just an ankle actuator, and you're trying to reduce metabolic cost while carrying a heavy load over uneven terrain, and you want to predict whether or not a particular device or actuation scheme is going to work, then you're going to need a predictive controller to make that calculation. So that's not so clinical, but you could make it clinical if you changed that to a stroke subject or getting out of a chair for an elderly subject. So there's lots of clinical applications for predictive controller. There's lots of questions we can't answer because we actually don't have predictive controllers. And you guys are pretty good at predictive controllers. I would love to see good predictive controllers. Yes? Yeah, so that's the question is, how are you going to model how the nervous system adapts to an actuator that you're wearing? And so that's why it's a grand challenge, right? A good predictive controller is going to have to predict how the nervous system adapts to a device. And so how is it going to do it? You tell me. Probably not very well at the beginning. So that's a real challenge. Yes, please. How can you calculate what? I see. So is it, how do we solve the redundancy problem? Yeah. So you always have to solve the redundancy problem. One of the things I showed you was there's lots of ways to solve the redundancy problem. Minimizing torques, torque squared, activation squared, metabolic cost. You can pose whatever you want, and then it just comes down to testing to see if that particular criteria you're using for a particular activity gives you reasonable representation of experiment. So we solve it by optimization. A lot of times there's so many task constraints that there actually isn't that much redundancy. And so you can use different criteria and you still get the same answer. In other activities, there's many unconstrained degrees of freedom. The null space is large. And so then you use different criteria and you get different answers. So it's hard to answer your question in general. So you just have to do it study by study. Yes, please. Yeah, so the question is, you may predict a change in loading. The subject may try to do this, but there may be side effects of that gait or other detrimental effects. And that is definitely a possibility. I mean, one of the things you can reduce the medial compartment load by pronating and turning your toe in and moving your knee medial, which is exactly the opposite of what they tell you at a running clinic, for example. So there certainly could be side effects. For the 12 subjects we looked at, which is an admittedly small cohort, they were pretty motivated to reduce their medial compartment load, and they didn't report any negative side effects. But it's a good point. You could definitely produce unwanted side effects by a gait modification because you're just optimizing for one thing, and you're going to have side effects. So it's a go. Well, you could compute them if you knew what you were worried about. You could put that as a constraint, reduce this, but don't increase hip load, for example. Yes, please. Yeah, no, it's fine. It's good. Okay, so the question is, for the analysis of muscle function producing a ground reaction force or a joint angular acceleration or a mass center acceleration, how can you be convinced that that's actually what the muscles are doing? And I'll tell you how we try to convince ourselves, because we're skeptics too. Just take mass center accelerations as an example. And that is the direction of the mass center acceleration caused by muscle is solely a function of the geometry, and that's it. So where the joint axes are and where the muscle line of action is relative to those and the foot floor contact model. That determines the direction. The magnitude is just determined by the muscle force. So you have confidence in the direction with respect to how confident you are in the geometry, and you have confidence in the magnitude with respect to how confident you are in the muscle forces. So there's uncertainty in both those things. So,
There's also a sensitivity aspect.
yeah. Yeah, so, and you can study the sensitivity, and if your conclusion is very sensitive to things you don't know very well, then you don't really have a conclusion. If, in contrast, mass center, for example, joint accelerations are frequently very sensitive to moment arms. Mass center accelerations are much less sensitive. So we end up being much more certain about the mass center accelerations than we are in joint angular accelerations. If you change the structure of the model, for example, add degrees of freedom of the spine, you don't change the mass center acceleration much, but you can change hip and pelvis accelerations. So we do these sensitivity studies, and we don't report conclusions unless the conclusions are insensitive to things that we're not certain about. The other thing we do to try to gain some certainty is we take the individual muscle accelerations and we add them up, and they have to add up to the whole body acceleration. And if you're not doing your analysis correctly, they won't. So it's a necessary condition. It's not a sufficient condition, but it's a necessary condition. The other thing we do, and others have done, is we stimulate muscles and measure the accelerations that they produce. And there need to be more of those studies where you compare directly the experimentally measured acceleration and your computed acceleration. So Daryl Thalen and his colleagues just published a nice study about hamstrings where they had a simulation and they stimulated muscles and compared them. It's probably like a 6-hour conversation before you'll be convinced, but. Yeah, one more question. Yeah, how you doing? Yeah, it's a yeah. So we do some of that. We aren't very good at it. But there's a collaboration with Andy Beweiner's group and Allison Arnold. They're doing buccal transducers, ultrasonography, and goats, and estimating muscle forces and muscle fiber velocities. And then, we were really interested in your ultrasound data for plantar flexors, for example, and compared ours to yours. So that's in humans, but you can obviously get more in animals. So there aren't a lot of groups doing it. Jonas Rubinson's doing it, and the Concord Field Station group's doing it. But it is a good opportunity to try to gain confidence. Great, thanks everybody.